Morning, guys. So through the last couple lessons, we've been introducing to you some of the math that we're going to be seeing in the remainder of this course here. We've been introducing to you unit conversion, so how the SI units, depending on the relative size of it, maybe adding a prefix, making the powers a little bit bigger or smaller can make the numbers a little bit easier to write. We introduced scientific notation to express really big and really small numbers using that order of magnitude. Make sure you can find that EXP and the EE button. I'm going to start off with a quick practice of a unit conversion problem, and then today I want to address the notion of rounding. I want to address the notion of significant figures. If you've done significant figures in chemistry, it's exactly the same, but again, I'm going to introduce it as if we haven't seen it yet. So let's just start off with a quick practice here. So just doing a quick conversion. I want you to see if you can convert for me. Convert 26 micrometers. Can you convert this one here into decimeters? Right. So hopefully by this time here you've had enough practice. So we're going to go question mark decimeters. That's the final unit that I want. In this case here I have 26 microns, so that means 26 micrometers, or 10 to the negative 6. What I want to do is I want to convert micrometer over to decimeter. What we saw from before here is it's usually hard to go from prefix directly to another prefix. Our solution or our strategy, however, was, well, let's just go prefix. Let's just go back to the base unit. I know micro is going to be a millionth, but it's a millionth of the base unit, not a millionth of deci. And what's nice here is I can just tack on another fraction. Let's get rid of that meter that still is there, and then let's go to decimeter. I'm now comparing each prefix with the base unit, and now I can just use the powers that I had memorized. So let's go through. Let's come up with one true relationship between meters and micrometers, which is bigger. Well, the meter is bigger, so 1 meter is equal to, even though micro by itself, if you check your chart, it would have been 10 to the negative 6, it doesn't make sense if I go a millionth, a tiny little number of a tiny little unit, it's one big guy, that doesn't make sense. By putting a 1 beside the bigger thing, even if my power would have been negative, it's not actually a positive power. I need a million, millionths of a meter. I need a really, really big number of a really tiny unit to make one big thing. On the other side as well, which is bigger, meter or decimeter? Well, meter is bigger. Likewise, deci would have actually been 10 to the negative 1, but now it actually is 10 little guys make one big guy. So overall, as long as we're dealing with metric here, it's just going to be simple powers of 10. 26 is going to pick up one power of 10. It's going to lose 6. So overall, I'm going to lose 5. So it's going to be here 26 times 10 to the negative 5. That's going to be my answer. That's not proper scientific notation because scientific notation should be the first unit between 1 and 9. I can move the decimal place one more, double check my numbers here. I can write that as 2.6 times 10 to the negative 4. And there we go. We've converted between one set of units to the other set of units here. Now, as we introduce to you the notion of significant figures in this lesson here, usually we're given a problem like this, where we're actually not the experimenter. Someone has just handed you a number like 26. We might need to interconvert their number or whatever. But the whole sort of big idea in this lesson here is we want to make sure that when we do conversions or calculations, whatever precision that this number had, I want to make sure that the final answer has that same precision. I don't want to suddenly have something that is way more decimal places than I can keep. I don't want to round it off. Well, this one was more precise, and then I just decided, yeah, who cares about that number there? The whole notion here is to figure out, how can I represent the final number to have the correct precision of the start? So, just beginning off here, and we're going to start off this notion here of significant figures, significant digits. We're going to start off just sort of with a thought experiment just to introduce to you this notion, what are significant figures? Let's imagine I have a pen, and I just lay the pen here on the side, and my experiment simply is measure the length of this pen here. So you take out your trusty ruler here, you line up one of the sides. This ruler here happens to not be a very good ruler. It happens to only have the centimeter tick marks. Right? So back in elementary school, maybe you use these rulers here. But still, we just go about it here. So it's 1, 2, 3, 4, 5, like that. Based on this ruler here, I've already lined up this side. I can ask a few people around the room, and I can say, well, how long is this ruler here? Some people might say 5.6. Some people might say 5.7. Some people might say 5.5, 5.6, right? There's a whole bunch of different readings. As we get this reading here, we're going to start introducing the fact. Notice that everyone is consistent with the 5. how come we're all consistent with this 5 here? Well, provided that I lined up this ruler here nicely, I can see that it's at least past the 5, but it's not quite past the 6. So this 5 here is going to be what's referred to as a certain number. That's going to be a number to definitely keep because I know it's at least 5. But now we are looking at the same pen here, and how come there is some variation? How come some people are saying 0.6 or 0.7 or 0.5? Well, that's because I don't have the millimeter tick marks. This part here does give me some information. It's telling me that it's going to be roughly sort of half in the next digit. But if you came back and said, oh, it's actually 5.4 or 5.5, I wouldn't be surprised because this one here is actually a guess. This one here is actually an estimate. That's a position that I'm not sure about. Is it any good for me if I take a number, let's say someone comes along and says, oh, I know exactly what it is. 5.7269341. Is there any sense in keeping so many decimal places? Hopefully you're able to say to me, no. Well, let's check it. I'm sure I know the 5. Because I don't have the millimeter check marks here, I'm actually guessing the 7 here. This could very well be a 5.6 or 5.8 or something like that. If this digit is off, there really is no reason to keep any other digits afterwards. Even if the calculator later on gives you all those decimals here, we decided to round it to one decimal place because that's not giving me any other precision. This number is said to have 2 significant figures. It has 2 digits of meaning. One of them is one that I'm sure of, the 5, and the other one, even though it might be off, it is giving me a ballpark. It's giving me some sense, yeah, it looks like it's going to be a little over half in the next position. I might be wrong, but it's giving you information. It is meaningful. Your friend comes along and notices, hey, your ruler's not really good. He lends you his ruler here. And this ruler here, as you might imagine here, has those 10 spaces, has those little millimeter tick marks. And what I'm going to do here is I'm just going to zoom in here. Let's say here's the 5. I go, right? So that's what the tick marks are. And let's say this pen here ends up lining up to about here, right? Now I would go back to the person and say, oh, the 5.5 was actually wrong. That's okay. I was guessing that 0.5 anyways, right? Now that I have a slightly better ruler, I should be able to read this distance in a little bit more precision. This time, if I line up the pen here, if I line it up slightly past the 7 here, it's not like the pen itself suddenly got longer just because I pulled another ruler. It's just because it's a more accurate and more precise ruler, it actually is giving me a little bit more precision, a little bit more truth to how long this pen is. So now if I ask a couple people around the room, you might say 5.71, 5.72, 5.70, right? All of these are measured in centimeters. Let's go through and decide which digits are certain. We'll notice that we're all in agreement with the 5, so that's definitely a certain digit. We're definitely going to be past this 5 mark. Because we now have the millimeter tick marks, now, depending on how you drew it here, well, I know I'm actually past the 7th tick mark. I'm actually confident about the 7. That's why there's no ambiguity, there's no variation there. And now, again, what I do is I keep around one extra guess. I keep around one extra spot. This guess here might actually be off. Some people were saying, no, it's spot on the line there. It's a 0 in this hundredths place. Or maybe it's a little over. It's not quite half here. Maybe it's a 1, maybe it's 2. This one here similarly is a guess, but you'll notice I've now picked up one more decimal place here. This number here is now said to have 3 significant figures. So significant figures here identifies for me how many digits have meaning. Again, if I did that example, would it do me any good if I said 5.72? Well, it's good for the 5, it's good for the 7 this time, but no good after maybe one more position. I would round off the rest of the decimal place. So let me just write down for you here what are significant figures, or also called significant digits. Significant figures are essentially the meaningful digits. These are the digits that you want to keep around. These are the ones that you don't want to round off unless you have to. The meaningful digits will contain all the certain digits, every ones that you're sure about. Well, if I'm sure about it, of course I'm going to keep around, and it actually allows you to have one guess. Not 2 guesses, not 3 guesses, one estimate. This guess here might totally be wrong. If you came back and said, no, it's actually a 0.04 or 0.05, I wouldn't be surprised because I was guessing it. But it is giving me some meaning. This is trying to hint at maybe I'm not quite half. I'm not really sure of that position though. So although it might be wrong, it has meaning. Right? Okay. So in that case there, right, great. Right, we have a 3 sig fig number, a 2 sig fig number. As a general rule, the more significant figures, the more meaningful digits that you keep around. Usually 3 sig figs, usually it implies more precise. We'll come back to that in tomorrow's lesson. Now this one here, in a way, it's easier because I was the actual experimenter. I told you the actual measuring devices. I told you how precise these rulers were, and you were just guessing off of this ruler. Many times, however, like the first problem, they might give you a number here. I didn't watch them take the reading. I don't know how good their measuring tools are, but I still have to associate how many digits of meaning when they write it in this fashion. So let's just switch gears a little bit here, and let's take a look at what are some rules for significant figures. And again, exactly the same as in chemistry. We're going to start off with some things that actually don't need significant figures. So let's start off here. Anytime you have a definition, definitions, and small counting numbers, these ones here are exact. These ones here are infinitely known, so they have infinite significant figures. So for example, if your mom tells you to go to the store and buy a dozen eggs, because that word dozen is defined to be 12, you know exactly how much to buy. Not 13, not 11, not 11.25, anything like that. A dozen by definition is 12. Earlier we said 1 micrometer. 1 micrometer is 10 to the negative 6 per meter. That's by definition. It's not a little over, it's not a little less than that. These ones here are infinitely precise. You can think of these ones here, let's say back to the 12 here, you can think of it as actually 12.0000000 to infinity. Because what we're going to be doing, later on when I see a number like 12, I might say that's just two significant figures. In this case here, because it's by definition, as I think 12.0 sort of to infinity, I think certain, 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 and I'm actually certain until infinity, so we can actually say this one here has infinite sig figs. These ones here don't need to worry about sig figs because they're precise. I define them to be that way. What about a counting number? Well, if I'm counting objects that are fairly easy, large size objects, if you trust my counting, these ones here should be fairly easy. So for example, let's say at one point I have 29 students in the room, right? Never gonna have 29.5 students, right? And again, if you just assume that I'm counting correctly here, I didn't miss any students here, that's an exact number. You can think 29.000 repeated, all right? So those ones there are just right off the bat. You don't need to worry about sig figs at all. The second type here, when they give me a measurement here, any numbers or digits 1 through 9, these ones are going to be assumed to be significant. So when they give you a measurement with any digits 1, 2, 3, 4, 5, 6, 7, all the way through 9, these are going to be important. So let's say they gave you a number 34.5 milliliters, right? They give me the unit to tell me this is a volume reading. Again, I didn't see what measuring tool they were using. I didn't see how precise it was. But based on a number like this, based on the rules that we're doing here, we can actually associate sig figs, and we can say, well, because 3, 4, and 5 are all between 1 and 9, all 3 digits are significant. This one here is a 3 sig fig number. It has 3 digits of meaning. What about that notion of certain and uncertain here? As I go left to right, I have all my certain ones. We're going to agree on the 30. We're going to agree on the 4 and the 1's position. I might actually be off at that 5. Maybe it's 34.4 or 34.7. But it still gives you some meaning. It's telling me it's roughly half in the last position. I won't keep anything beyond this. So even though these 3 digits have meaning, that third digit, the one that's farthest to the right, is always my guess, and that one there might actually be wrong. What digit am I missing? Right? If 1 through 9 are always important, this is easy. The digit that I'm missing here are zeros. Now here's the problem with zeros. Sometimes they're important, sometimes they're not important. In the olden days in physics, they would have gotten you to memorize a whole list of rules. They would say, well, if it's a no decimal place number and it's a trailing 0, it doesn't count. When it's a 0 between things, it's a whole list of numbers that I wouldn't bother you with. What I find helpful here is to identify whether zeros are important or not important. We're going to use an arrow rule. And essentially, there's only sort of 2 steps to this arrow rule here. Essentially, you're going to imagine like a bow and arrow. Imagine an archer. This arrow here is going to shoot. It shoots left for numbers without decimals. And the only difference is the arrow shoots the other way. It shoots right for numbers or measurements with decimals. Instead of memorizing lists and lists, paragraphs and paragraphs of rules, you just need this one rule here. So let's just start off here. Let's take the number like 500. Maybe it's like 500 milliliters, something like that. Again, I'm not the experimenter, so I don't know how precise they are. Based on the rules I have so far, The 5 is between 1 and 9. I know that's significant. At the very least, it's going to be 1 sig fig. The question here is, are these zeros in such a way that they actually add significance? They actually add rules. So let's just try this arrow rule here. This number does not have a decimal place, so I'm going to imagine standing on the right-hand side here, and I'm going to shoot left. The rules for this arrow is it can cut through any number of zeros. When it runs into the first thing that's not a zero, it gets stopped. So imagine taking a bow and arrow here. This arrow here, you fire it. Okay, it cuts through those zeros, no problem. It runs into the 5 and then just gets cut off. If the arrow has cut through the zeros, it's trying to tell you these zeros are insignificant. These zeros here are not important. They don't give you any extra meaning. These zeros, the ones that are insignificant, are called placeholders. What's their job then? Why did I need them here? Their job is just to make sure the 5, the one and only significant figure that I have, is in the hundreds position. So I want you to be careful. The number is still 500. It doesn't suddenly become 5. But at least in terms of this meaning, in terms of this rounding here, it's only one significant figure. So 1 sig fig here. So very low precision. This means the one and only digit that I have is actually a guess. We may be talking 600, we may be talking 400, right? But the unsure is at the hundreds position. Again, I want to emphasize, I have not suddenly made the number 505. If you go to the pizza store and you order 500 pizzas, that's very different from ordering 5. When I say that they're insignificant or they're not important, I'm just saying they don't introduce any other precision. They don't introduce any other meaning. What if I wrote that number 500 slightly differently? I wrote the number 500.0. How many significant figures is this way of writing 500? Again, numerically it's still 500. This time, because we do have a decimal, the arrow has to go the other way. So imagine you're standing this side here. This arrow here is going to shoot to the right. This arrow is not going to get very far. It gets stopped at the 5. Remember, you only get to fire this arrow once. Anything that the arrow has not cut through are now significant. Now we have the exact same number 500, but this is now represented as having 4 significant figures. In general, the more significant figures, the more precise it is. Looking at the language of sort of certain and guesses, I'm certain about the 5, certain about the 0, certain about the 0. Where I'm guessing is actually that last position. So this time, I'm not sure, did I order 600 pizzas or 400 pizzas? This time, no, I ordered 500 pizzas, but maybe 500.1 pizza, 500.5 pizzas. This could even go 499.9 pizzas as well, right? It's still sort of up and down from this number 500. It's the same 500, but that number is written to more precision. Especially in chemistry, we do this annoying thing here. Let's go 500 with the decimal. Usually you only have a decimal if it's point something, right? That's the only reason why I have that decimal. But in this case here, in terms of significant figures, because this number here also has a decimal, the arrow still shoots to the right, it still gets stopped by the 5, and now I have 3 significant figures. So that means you go to the pizza store here, you're still intending to buy 500. I'm sure I want to buy 500. I'm sure about the tens position being 0, but I want to buy maybe 501 pizza, 499 pizza, things like that, right? So the numerical value is always 500, but what I'm changing here is in giving you this number written in different ways, it's showing you a different precision to it. I've done this number 500 as having 1 sig figs, 3, and 4 sig figs. How would I write this if I was unsure? Let's say I go to the store, I want to buy 500, but I want the guess to actually be the tens position. I want it to be like, oh, maybe it's 510 or 520 or 490 or 480. What if I wanted to be unsure at that tens position? We now have a problem because if I had no decimal, 1 sig fig. Even with this funny decimal with nothing afterwards, that's already 3 sig figs. How can I show you that actually my guess is actually in the tens position? Here at this point, we introduce one last rule and we say, for scientific notation, all base numbers in scientific notation, and it has to be correct scientific notation, or exponential form, are significant. So I want to make sure that I keep the number as 500. I can write this one here as 5.0 times 10 to the 2. I can separate off the order of magnitude. That just puts the decimal in the right place. And then now I actually have, this is my base number. My base number happens to have 2 digits. This one here now says we're unsure at that tens position. So if you're ever having trouble writing significant figures, rounding to significant figures here, you just basically write it in scientific notation, right? So far we've introduced to you what are significant figures. The more significant figures, the more precise it is. And especially when we're not the experimenter, we treat digits 1 through 9 as important. Zeros are a little bit annoying. Sometimes they're important, sometimes they're not. But now we sort of know how to associate how many digits have meaning. Now finally, I'm going to start introducing to you some calculations. Right? Normally in science, you just don't take a reading and just leave it like that. Usually we operate on that somehow. Especially in this case here, we're going to find we're actually smarter than our calculators. The calculators generally don't know about significant figures. They didn't know that the numbers that you're crunching into are actually measurements. We're actually going to have to do the rounding ourselves. For our calculations here, we're going to separate our rules into two. One set of rules is involving adding and subtracting. Usually when people sort of list this rule here for adding and subtracting, we just want to round our answer. We round to the least decimal places. I'm going to correct that a little bit here. In fact, when you say least decimal places, what you're actually saying is you're rounding to the least precise position, the least precise spot. It's just saying least decimal places is a little bit easier to memorize. So let's just look through a quick practice question or two here. Let's take the number 1.2 centimeters. Let's add it to 3.45 centimeters. Right? So super easy. I want you to pretend you're back in elementary school here. I'm going to line it up here, 1.2 added to 3.45. If you had to use your calculator, or you can just do it in your head here, this gives you 4.65 centimeters. That's where your calculator will spit out. Because in the calculator, when you type in 1.2, it thinks exact 1.2. 1.2, it thinks exact 3.45 when you type that in. That's why it gives you exact 4.65. Now when we do this rule here, we say, wait a second. These ones here were actually centimeters. These ones here were actually measurements. These ones here are actually sort of plagued by significant figures. We can never know the real value of a number because it just depends on how good my measuring tools are, how good my eyeballing, estimating, interpreting my values are. So what I'm going to do here is I'm going to say 1.2. This number here has 2 sig figs. I'm certain of the 1. I'm actually unsure of the 2. Maybe it really was 1.3 or 1.5. I'm not sure. The 3.45 was like my better ruler. My better ruler here, I was actually sure of the 3, sure of the 4. Remember, I'm always allowed to keep around one guess. The guess is always going to be the one that's farthest to the right. In this case here, my guess is going to be that 0.05 position. When I look at this then, my calculator numerically gives you 4.65 exactly. But I want to look back, because these are measurements, which of these guesses is actually worse? Which guess, if that position were off, there really is no reason to keep anything afterwards. In this case here, it shouldn't be that hard for you to find here. The tens place here, if this one were really a 1.3 or 1.4, that would knock off the first decimal place. Then it would really not care what the digits afterwards are. So using the decimal place rule, you can say 1 decimal place number. This is unsure of the second decimal place. Even though the calculator gives you a 2 decimal place number, I want to round it back to having 1 decimal place. So that guess there is worse. Because that's already my guess, there really is no sense of keeping anything afterwards. We do our regular rounding here. In this case here, because it's a 5, we're going to round this to 4.7. There was a while in science that if we had a perfect 5, we used to round it to the nearest even. So the nearest even was actually 4.6. The hope was half the time I would end up rounding down, half the time I'd round upwards. Hopefully it'd give me somewhere in the middle. Nowadays, we just round everything up. So 4.7. So even though the calculator gave me 4.65, using the lens of significant figures, knowing that, these are actually measurements, these are actually plagued by sig figs, we actually need to re-round it so that it represents the correct precision. Let me show you an example where this decimal place rule actually fails. So let's take 100 milliliters, that's minus 23 milliliters. You can either do that in your head or a calculator here. 77 milliliters, easy. Right? And in fact, even if you line it up, 100 minus 23 gives you 77. If you use the decimal place rule to the letter, it seems correct. Because you would say here, well, this number here has no decimal place. This number here has no decimal place. Well, the one that has the least decimal place, well, it's still 0. Great, my answer is 0 decimal place. But let's analyze it a little bit more. When I have a number like 23, which of the digits is a guess? Remember, the guess is always the farthest one to the right. The number 23 is a 2 sig fig number. That means this 3 is actually a guess. The 1's position might be off. I may be pouring out 24 or 22 or 21. I'm not sure. How about the 100? The 100 is actually a 1 sig fig number. So the one and only digit, that's not a 0, The one and only digit that I have is actually a guess. We may be going to the store and buying 200 or 300. I'm not really sure of this 100. We're going to use the same sort of idea here. Well, if one of them was going to be off, and that would actually knock off this position, there's no reason to keep it anything afterwards. In this case here, because the numbers happen to be a little bit bigger, my decimal places really doesn't do it justice here. In this case here, if my hundreds is off, that would actually knock off the hundreds position. There really is no reason to keep anything afterwards. This digit here is bigger than 5, huh? If I had to round it back up this way, 77 rounded, it's going to be 100. That's exactly what I want you to say. 100 minus 23 is 100. Huh? This is weird, right? Why is this significant figure stuff so strange? Let me give you a sort of a thought experiment at where this might come up. Let's imagine I take a volume out of a grad cylinder. This grad cylinder here has only one mark. It only has a mark 500. I fill in some water. We're supposed to read the bottom of the meniscus here, and I basically ask you, well, how much water is in there, right? You guess, about 100, right? Could it be 200? Sure. Could it be 300? Maybe, right? But I'm really not sure. It's hundreds, really low precision. What you do in this experiment is you definitely dump out 23. So take this grad cylinder, you pour it into another grad cylinder. This grad cylinder here has more markings, and we can actually measure out, because it has more markings, 23 is actually left. It is true that this volume here has decreased. But now what if I ask you the question again, looking back at your original grad cylinder, how much liquid is in there? Do I know that it's any better than 100? Well, maybe I was actually 200, and maybe by dumping it out, maybe I'm actually closer to 100 now. That's actually what this math is saying. Even though we're taking 100, because this 100 has such low precision, maybe that were 200, maybe it's only after you toss out some solution, maybe afterwards we're actually closer to having 100 there. And that's that notion here. I'm treating the least precise digit. The least precise, I'm guessing at the hundreds, I'm guessing at the ones. The least precise is the hundreds, so I need to round it back to the hundreds. Just like if it were decimal places, the least precise is the tenths position, first decimal place. This one is the second decimal place. No matter what my calculator gives me, calculator doesn't know about sig figs, I want to round it to that least precise spot, the least precise figure. Now, fortunately for us, usually we are dealing with decimals, so usually decimal place is a nice, easy way to remember it, but just remember that idea. I don't want to have a final answer that's somehow more precise than what went into it. Let me end off just introducing to you the multiply-divide rule. So a different rule depending on your operation here. When you multiply and divide, what I want you to do is I want you to round your answers, round to the least significant figures. So the way people memorize it here is for add and subtract, they do decimal places. For multiply and divide, they do significant figures. So let's try it out here. Let's try 5 centimeters multiplied by 7 centimeters. Right? If you type that in your calculator, calculator spits back exactly 35 because it didn't know there was any uncertainty. It thought exact 5 multiplied exact 7 is an exact 35. However, when we do this sort of rule with rounding to least significant figures, this is only a 1 sig fig number. This one here also only has 1 sig fig. I can't suddenly have a number that's 2 sig figs that's more precise than these ones were going into it. So if I'm only allowed to keep this one here to 1 sig fig, you read left to right, I'm only allowed to keep this digit here. The 5 rounds upwards. 5 times 7 is now 40. Right? And that 40 is understood. It is only a 1 sig fig number. Maybe it's down to 30 or 20 or 50 or whatever, but it's so low precision. Right? You can't say, well, it really is 35. It's because these ones here really were so low precision. If this 5 were actually a 6 instead, 6 times 7 is 40s, so writing as 40 is actually not too bad. So just be careful. When you multiply and divide, the numbers get big really fast and get small really fast. Instead of trying to line up the decimal place, it's a little bit easier. You take the answer out of the calculator and you round it so that it has the precision of the least sig figs. So let's do this one more time here. Let's go 5.00 times 7.000. Calculator says, all right already, this is 35, right? Because the calculator thinks exact 5, exact 7. However, when we do our significant figures here, these are numbers that have decimals, so the arrow just sort of cuts from the right here. This 5.00 has 3 sig figs. This 7.00 has 4 sig figs. The least precise one has 3 sig figs. Even though the calculator wrote out 35, thinking 35.000, it now only looks like 2 sig figs. I actually want to come along and I actually want to add a 0.0 so that this figure here actually does have 3 sig figs, so that I'm certain of the 3, certain of the 5, and then I'm actually guessing that 0.1, 0.2, that position there. So try out your worksheet here. Just practice playing around with doing sig fig rules for add and subtract and multiply and divide, and we'll pick it up from there tomorrow. Thanks, guys. Take care.